Hello. In the previous lecture, we were talking about exchange interaction and we introduced ferromagnetism, antiferromagnetic structures. Principally, this was indeed a very important lecture for this course. And today we continue having this information, having this knowledge. We can switch to main families of ferromagnets, ferrimagnets, and antiferromagnets. So today we are going to speak about rock salt structures, about ferrites, garnets, perovskites, and a bit about barium hexaferrites. So there are 5 classes which we'll discuss today, and I should warn you that all of them are insulators. So these are not metal. So there are no free electrons, and we can use the models. The Heisenberg model, which we represented, which we discussed in the previous lecture, we can use now to describe magnetization. So, and the first one is rock salt structures. This structure is also known as sodium chloride structure. It is commonly found in the transition metal monoxides like manganese oxide, iron oxide, cobalt oxide, nickel oxide. The point is that all these structures are antiferromagnetic. For example, nickel oxide is one of the classical antiferromagnetic materials which are used nowadays also intensively in cutting-edge research on spintronics, for example, in antiferromagnets. And the first what we need to introduce are Nil temperature. We already know, yeah. So Nil temperature is analog of Curie temperature, but for antiferromagnets, and usually Nil temperature for them is below room temperature. But for the last one, for nickel oxide, it's above. That's why this material is used in lab pretty often. So what is the crystallographic structure of this material is FCC, face-centered cubic lattice. And this transition metal ions are separating from each other along the cube edges by the oxygen ions. So we can have a look here. So here's oxygen, manganese 2+, for example, and you see that manganese forms FCC. So we have here these 4 atoms and one in the middle of each phase. But in addition, we have oxygen O2- ions staying here in between. So usually for all the structures, these materials we're going to speak today, is the crystallographic structure is quite complex, but we don't need to go into the so details. It's just important to get general understanding what is a structure. So here it's cubic in such an arrangement, and here in this figure you see how spins, magnetic moments of manganese 2+ in this case, are oriented. So as we discussed, this antiferromagnetic order. So in this plane, all spins are pointing up, and in the neighboring plane, spins pointing down. Therefore, it's antiferromagnet. And we will just watch a movie about general structure of these materials.
Let's see the structure of NaCl. Radius of a sodium ion is 0.95 angstrom and that of chloride ion is 1.81 angstrom. The radius ratio of sodium ion and chlorine ion comes out to be 0.526. The radius ratio suggests that coordination number of each ion is 6.
The crystallographic
So
structure
in
is the same.
NaCl structure, each Na+ ion is surrounded by 6 Cl- ions. And similarly, each Cl- ion is surrounded by 6 Na+ ions. As you can see, each sodium ion is octahedrally surrounded by 6 chlorine ions. If we extend the cubic structure, we can also see that each chlorine ion is octahedrally surrounded by 6 sodium ions. Total number of chloride ions per unit cell is 1/8 of 8 chloride ions at the corner of the cube and half of 6 chloride ions at the face centers of the cube. So total number of chloride ions per unit cell is 4. Number of sodium ions per unit cell is given by sum of 1/4 of 12 sodium ions at the center of each side of the cube and 1 sodium ion at the body center of unit cell, which equals to 4 sodium ions per unit cell.
Okay, so that was it about the crystallographic structure of these materials, which we name rock salt structures. And we are moving to the next. And next structure is Spinel structure compounds, or also they are known as ferrites. Ferrites are used a lot in our application, micro and so on. And therefore, let's speak about. So ferrites are usually ferromagnetic ceramic compounds. So it means that it's uncompensated antiferromagnet derived from iron oxide. So very typical example of ferrite is magnetite, iron 304, and as we discussed, it's a material which gave a name to the magnetism. So it's ceramics. It's very hard, brittle, and it's bad conductor of electricity, so it's isolator. Many ferrites adopt the Spinel structure with the formula AB2O4, where A and B represents various metal cations, usually including iron. Or sometimes in different literature, so here is a mixture of information from Krishnan and from Wikipedia. Krishnan, for example, represents this formula slightly different. He's putting MO as one part of chemical formula than iron 2O3. And M here, it represents a divalent cation. Good. What about crystallographic structure? So it's usually cubic closed packed FCC structure with R cations occupying 1/8 of tetrahedral holes and B cation occupying half of the octahedral holes. So it's also getting a bit complex, but let's have a look here. So metal ion in the tetragonal sides are shown here with these black points. Then we have metal ion in the octahedral side with small atomic structures here. And of course, we have here oxygen. Oxygen is shown with large ions, with such large circles. So this is approximately what is it. Also, we have here a cubic structure. Most of the structures are cubic, except the last one, which is hexagonal, which we'll consider today. And again, we are moving to movie, which will tell us where ferrites are used. But before we'll do this, let me just introduce you the main types of ferrites, so which are used nowadays. So you see, these are the examples: nickel oxide, iron 203, zinc oxide, iron 203, MgO, and then there are more complex materials. So here you can see how many ions give magnetic moment. So here, for example, iron 3+ gives you 5 board magneton in one direction. So octahedral sides, so magnetic moment from tetrahedral and octahedral sides, they will be in oriented in opposite direction. So it means this is ferromagnet. So the total magnetic moment will be kind of sum of, actually you need to sum all of this, 5 spin up to nickel spin up and 5 down. So it means that this iron 3+ from octahedral side will compensate 5 spin up from tetrahedral side. So magnetic moment of this material will be coming from nickel too. But this is only for this structure. You see for zinc it's different. This one is antiferromagnet. Here you can see net magnetic moment in magneton board. So here's 2. This is antiferromagnetic, it's 0. This one also has quite small magnetization. This one has slightly larger magnetization. Yeah, so this is about the crystallographic structure, and now where it's used. Again, video, I think this one is a bit longer, but.
Ferrites. Ferrites, or the stones that could attract iron, were discovered before the birth of Christ. These stones were found in the district of Magnesia in Asia Minor, hence the name magnetite. Navigators used magnetite as lodestones to locate magnetic north. Naturally occurring magnetite is a weak, hard ferrite. Hard ferrites are permanent magnets. In 1946, J.L. Snowick of the Philips Research Laboratories in the Netherlands succeeded in producing soft ferrites. Ferrites are mixed metallic oxides of high resistivity and are the members of the semiconductor family. They are ceramic ferromagnetic materials with the general chemical composition MoFe2O3, where M is a divalent metal such as iron, manganese, magnesium, nickel, zinc, cadmium, cobalt, copper, or a mixture of these. The most common ferrites are listed here. Ferrites are manufactured by homogeneously mixing various iron oxides and then calcinating the mixture. This causes the partial decomposition of the carbonates and oxides. This mixture is then sintered. This is done by gradually raising the temperature to 1500 degrees centigrade in a kiln. Typically, the cores will shrink by 10 to 20% of its original size after sintering. The mixture crystallizes into a cubic structure. The resulting ferrite has a hard black and non-porous ceramic appearance. Ferrites are used to reduce the losses due to eddy currents because of its high resistivity. Let us now discuss the important applications of ferrites. Ferrites are used as cores for inductors and transformers. Electric generators and electric motors use fixed magnets, and ferrites are ideal for these applications. Cassette and videotapes use ferrite-coated plastic base to record the signal.
I'm too old, I still
They are used in radio and communication equipments, microwave devices, and in digital computers. A ferrite rod is inserted into a coil of wire acting as an antenna to concentrate the electromagnetic energy into its core.
Okay, so that's it about ferrites. Now we are reaching to the third class of materials, which are named garnet structures. So garnet, it's mainly speaks us about the crystallographic structure. So it's again complex cubic structure, and garnets. This the same, in jewelry they also use garnets. You can have it depending on chemical composition. You can get probably any color you want, and this is a stone of the same structure. But of course, we are interested in artificially created materials which have that properties, that magnetic properties which we need. So the iron-based magnetic garnets are cubic ferromagnetic insulators that have the formula 5 iron 203, 3 M2O3. So such split it again into two parts, and M here can be represented by trivalent ion. You can see here, so principally many different ions can be. Or more commonly, you can meet the chemical formula in this form: M3, iron 5, oxide 12. Yeah, so again, this is cubic structure, and you can split it in such formula: M3, 3 plus, iron 2, 3 plus, iron 3, 3 plus, or 12. And different brackets represent the dodecahedral 24C, octahedral 16A, and tetrahedral 24D sides. So that you understand, this is a very complex cubic structure, and in each unit cell, we have 160 atoms. Or we can also, people often speak about primitive cell, which is twice smaller than unit cell in this case, and then we're talking about 80 atoms per unit cell. So here you see different materials. So this would be our YIG with yttrium, but you can have any different materials, and then you can see the Curie temperatures. All of them are above room temperature, and then you can see also saturation magnetization value in amperes per meter. So principally, YIG has the largest saturation magnetization. Oh no, also lutetium is also large one. Okay, and now I'm coming to yttrium garnet. It is one very popular and interesting type of garnet. In particular, I'm investigating a lot spin waves, and for spin wave, it's very important lifetime. So when you excite spin waves in some materials, they can exist only a certain time, and we need to search for material where these waves exist as long as possible. And although yttrium garnet was invented, I think, around 60 years ago, it's still the absolute champion in terms of spin wave damping, because waves exist there for hundreds of nanoseconds, and that's why it's very interesting and very popular nowadays. Also, and so here you see its name, yttrium garnet. You usually say simply YIG. Here you can see its chemical formula: yttrium-3, iron-5, and 12 atoms of oxygen. And here you can see that sometimes you write it in such term, where these 5 ions of iron are splitted into 2 parts, because 2 of them are sitting, so 2 and 3. One part is sitting in octahedral site, and another sitting in tetrahedral site. So it has such a complex cubic structure, and iron atoms can sit in different sides of the structure. And why these atoms ions are interesting? So here you can see the the atomic structure of iron 3+. And you can see that the 3D shell is exactly half filled. As we know already from Hund's rule, all spins will be oriented along, so the spin angular momentum will be maximized. It will be 5/2 from one ion, sorry. But if to speak about orbital momentum, you can count it +2, +1, 0, -1, -2. In total, it will be 0. This is very important because spin-orbit interaction, there is such phenomena which we'll discuss in the second lecture on spintronics. It's very important, staying behind many physical mechanisms like crystallographic anisotropy, spin Hall effects. So there are many effects based on spin-orbit interaction, but also spin wave damping related to spin-orbit interaction. So it increases damping. Therefore, what we want to have material with minimal spin-orbit interaction, and its energy is proportional to the multiplication S times L. That means if L is equal 0, then theoretically, of course, you will get 0 spin-orbit interaction in this material. But the truth is that spin wave damping is really small in this material, and especially it's also related to the fact that it's insulator, so we have no free electrons here. Good, and now let us have a look again on these ions. You see that they are coupled in between through oxygen. And we know that in the structure, we have to speak about so-called super exchange interaction, which plays magnetic moments from ions antiparallel. So it's kind of antiferromagnet, with the difference that in one sublattice we have 3 ions, and in another 2 ions, I'm sorry, and in another we have 3 ions. So it means that we have 3, which 2 of them are compensated by another. So for the whole chemical formula, we will have magnetic moment from one iron 3+ ion, which is S equals 5/2. Having this information, it seems that we have in primitive cell 20 ions, iron 3+, 12 oriented in one direction, 8 oriented in another direction. You have the magnetic moment. So per primitive cell, you will get then 20 magneton Bohr And then simply when you know the lattice constant, so it's a huge material with 80 atoms per primitive cell, and this is the lattice constant of this material, then you can do the simplest mathematics, and you can calculate what is the saturation magnetization for yttrium iron garnet, but of course at 0 temperature. So this is a garnet, and let's see very brief video about garnet. It's not juveler garnet, it's not yttrium iron garnet, it's just some standard garnet, and there will be a brief discussion of it.
This is garnet. Garnet is a pretty common mineral in metamorphic rocks, and you can tell it by its color mainly. It's usually this kind of a deep reddish brown, almost a burgundy color. And that is the main way that I notice it. If you see it in a rock, it'll probably have an interesting crystal shape, like a little dodecahedron. They look like little round balls. If it's a larger piece like this, one thing that can fool you are these things that look kind of like cleavage surfaces. But they're not actually flat enough to call a cleavage surface. It's more of a parting, and that can be kind of fooling. The other thing to look for is it's very hard. It's about an 8 on the hardness scale, so it should easily scratch the glass, and should probably even scratch a piece of quartz if you have a nice flat piece. So very hard,
as hard
used
as
for
diamond
sandpaper,
almost,
and very much this color.
But if you drop it on the floor, which I successfully did and was a student, we will have many pieces of this material. Okay, good, and we have move on.
This is garnet.
To the structure named Perovskites. Again, another family of new family of magnetic materials. Very interesting. There is a huge field of science nowadays which is investigating perovskites because of their rich physical properties. And these compounds are derived from the mineral calcium titanium oxide 3 and have the general formula M iron O3, where M is a large cation such as lanthan 3 plus, barium, calcium, strontium, and so on. Manganese or calcium can also replace iron to give size structure. M manganese O3 or M cobalt O3. So instead of iron, you can have manganese or cobalt. So in the perovskite unit cells, the large cations form a simple cubic structure with the oxygen anions occupying face-centered positions, and the smaller cations, iron, manganese 3 or 4, occupying the body centers. For example, here again cubic structure. We have here oxygen, these open circles. We have lanthan here sitting in the middle, black dot, and this bold circle, these are manganese. So this kind of structure they have, and there is a nice real advertisement movie which I liked about perovskites, but you see it's done by science journal, so it's obviously high quality and with properly selected content. So let's have a look. It's a bit longer, but I think it's worth investment of the time.
Perovskite is one of the most common crystal structures found on the planet, but common doesn't mean boring. While it was originally discovered as a mineral, this amazing crystal shape shows up everywhere and is a common subject for cutting-edge scientific research. For starters, Earth scientists are fascinated with it, because even though it's the most abundant kind of mineral on the planet, we hardly ever see it. Most of it is buried deep within the Earth's mantle. Perovskites make up 93% of the lower mantle's mass, and 38% of the total mass of the planet. There are several different kinds of perovskite, but they each share a similar dense crystalline structure. In the mantle, silicate perovskites are the most common. The high density of these minerals create the sharp boundary at a depth of 660 kilometers that separates the less dense upper mantle from the more dense perovskite-rich lower mantle. Below 2,600 kilometers, the pressure crushes silicate perovskites into a new mineral called post-perovskite. Post-perovskite is mechanically weaker but has a higher electrical conductivity that allows pockets of the mineral to interact with Earth's magnetic field. Researchers theorize that all terrestrial planets bigger than Mars have a similar abundance of perovskites deep beneath their surface. So mapping out these mineral transitions allows us to not only learn more about the internal structure of our planet, but other planets as well. Perovskites' knack for conductivity brings to the fore another quirk that makes it the perfect target for research. Metal halide perovskites are a type of crystal that can act as a semiconductor, so scientists are looking at how it can be incorporated into various technologies. In 2009, researchers discovered that by shining light on perovskite, they were able to induce a small electric charge, creating a minuscule solar cell. Since then, the efficiency of perovskite-based solar cells has increased to over 22%. These panels generate electricity via a thin layer of lead halide perovskite film on top of a coating of conductive oxide. One of the benefits to using perovskites in solar cells is their defect tolerance. Unlike silicon cells, where everything has to be aligned perfectly to work, and any damage renders the entire device unusable, perovskite cells can be simply layered onto a surface and generate an electric charge, making manufacturing easier and cheaper. But while engineers are hopeful that perovskite could help to bring down the price of solar energy, they have some downsides for now. The perovskite cells are small, fragile, and degrade much faster than conventional silicon crystal panels, on the order of hours and days, instead of years. If perovskite can take in light, could it also make it? Researchers are looking into improving screens and LEDs, using lead halide perovskites as quantum dot nanocrystals. On an LCD TV screen, pixels are made up of 3 colors: red, green, and blue. Tests with prototype perovskite pixels used a single kind of light source, blue LEDs, with perovskite polymer beads on top to control the color. When the blue light shines through the beads, the color of the light that makes it through comes out in a green or red hue. While silicon quantum dot displays are out on the market already, they are very expensive. So, like solar panels, using halide perovskites could bring down the cost of manufacturing immensely. The colors created by this perovskite prototype exceeded some television and computer monitor standards, good enough for use in a future TV. Even though each of these uses has some roadblocks to adoption, the massive increase in research and studies about perovskite means we'll be seeing a lot of this crystal structure in the years to come.
Okay, that's it. Good. Now we are switching to the next type. It's hexagonal iron oxide structures. So, as opposed to all previous structures, we do not have any more cubic structure. It's hexagonal, and the simplest structure is based on the molecular composition barium iron 12 oxide 19. It's known as barium ferrite. Its structure is isomorphous with mineral magnetoplombite. So here lead oxide is a 6 iron 203. And yeah, so this oxide was originally developed as a permanent hard magnetic material for magnetic recording, and is easily prepared by bulk ceramic processing methods. So also this hexaferrites were, at least in the past, were used widely for magnetic recording. For example, now I'm not so sure, but I'm pretty sure that in some applications it's still used. Yeah, so if to speak about crystallographic structure, instead of showing a picture from Krishnan, I have found in this paper, Moitra et al., some color-coded figure where you can see that many different ions. And from them, let's start from here. Smart green spheres represents oxygen atoms. This little bubbles here, this is oxygen. White, while larger cyan spheres represents barium iron. So this is barium. This is oxygen. And all the rest, these are our iron, where it's written. Iron atoms, yeah? So red, pink, gray, blue, and yellow, these are all iron atoms which are sitting in different sites. So this is a very complex structure with many different sites where iron is usually occupied, but in addition we need barium and oxygen. And these materials are also well known that they have very strong crystallographic anisotropy. So we do not discuss crystallographic anisotropy, magnetic anisotropy in this lecture, but it exists. So there is light and hard axis of magnetic material. So sometimes you take piece of magnetic material and it wants to have it oriented along this direction. And kind of if it's sphere, for example, it's not clear why it doesn't want to put here. And the reason is crystallography. Then from all possible crystallographic axes, magnetization, we choose that direction where total energy will be minimal. And this is named light axis. And this hexaferrites, they have very strong anisotropy. So it really will be hard to push if you take piece of magnetization pointing in that direction along some crystallographic axis. Then you apply field, you want to pull it out. And this is hard to do. So you need to apply large field. That's why magnet is named hard. And again, we look about application. This video is slightly different. This one is from Fujifilm about technology. It's new technology for me. It was interesting to learn, but it shows you about technologies which are already in industry, but still, to my understanding, it's not really used so much. But let us have a look.
Making use of world-class technology cultivated through the production of photographic films, Fujifilm has continued producing magnetic tapes that have always been at the forefront of technology. The surface of magnetic tapes are uniformly coated with tiny magnetic particles, whose S and N magnetic polarities represent the zeros and ones of digital signals when recording data and reading back data via the reverse process. The company has strived for years to hone its technologies in pursuit of high performance by coating magnetic particles on tapes with greater uniformity and density, making the surface of the magnetic layer as thin as possible and miniaturizing magnetic particles. Then, Fujifilm succeeded in developing magnetic tape using barium ferrite magnetic particles, implementing unique technology. Compared to traditional metal tapes, barium ferrite tapes have high capacity. Barium ferrite has miniaturized magnetic particles to less than half at what it traditionally was, giving a massive boost to data storage capacity. This was made possible by its unusual shape. Traditional magnetic metal particles had to be elongated in shape to maintain polarization. But changing their shape to achieve miniaturization weakens their polarity, destabilizing their ability to store information. Miniaturizing them while retaining their shape also results in chemical instability caused by the thinning of the antioxidant layer. On the other hand, the magnetism of barium ferrite relies on its hexagonal crystalline structure. This means that miniaturization does not lower its magnetism. Moreover, barium ferrite is already oxidized, so it does not require an antioxidant layer, enabling further miniaturization. Long life. As the main constituent of barium ferrite is an oxide, it doesn't deteriorate through oxidation, giving it an expected lifespan of 30 years or more. High reliability. Tapes using barium ferrite have better frequency response, greater magnetic recording, and reproduction accuracy. This boosts the lifespan of the tape drive and achieves greater stability during the reading and writing of information. Barium ferrite was adopted for a tape product for a high-end enterprise system in 2011. In 2012, it was implemented by Fujifilm for use in LT06 tapes. In 2015, the company successfully developed the technology for a magnetic tape capable of storing 220 terabytes. The future of tape archives lies in barium ferrite.
And we are ready for the next lecture about magnetism in metals and alloys.